Hi everyone, I am Dr. K. Kannan, Assistant Professor, Department of ECE, R.M.K. College of Engineering and Technology. Today I am going to talk about the important topic of optical communication is ray theory transmission. So first of all, we know that what is optical fiber communication? It is a method of transmitting light signal from one place to another place by using a optical cable as a medium. So that is called optical fiber communication. And in this optical communication, the data transmission by using the light form is between the wavelength of 800 nanometer to 1300 nanometer. Now, today we are using the wavelength range still 1550 nanometer. So, as I told you, the communication between two places by using optical fiber in the form of light. So, what are all the main characteristics of light is first one, intensity of the light. So, what is the intensity of light? Then frequency of light. And third one, wavelength of light. And fourth one, spectral width of light. So, these are all the main characteristics of light signal. Then light acts as an electromagnetic waves where the polarization is maintained between the sending place and receiving place. Then what are all the structure of light sources? So there are three model is available or three structure is available. First one, it is simplest model of ray theory, that is called a ray model, and advanced to that simplest model is called wave model. Then the more advanced version from simplest model and ray model is called wave model. The another name for wave model, it is quantum theory. Then ray theory transmission, or we can say that it's a ray model. So in this ray theory transmission, first we should understand what is a ray optics. So ray optics, it is an ideal model of light. It is obtained by choosing a line that is perpendicular to the wavefront of the actual light and that points in the direction of energy flow. That is called ray optics. Okay, so what are all the types of ray optics available? So in the types of ray optics, first one is called meridional ray, and the second one is called skew ray. Third one is guided ray, and last one leaky ray. So these four different type of ray optics available in our ray theory transmission. So based on the wave flow from transmitter to the receiver, we can have four different type of ray optics. Then we'll see what is ray optics. So in ray optics, as I told you, there are four different method. First one, meridional ray. Meridional ray, it is a ray that passes through the axis of an optical fiber. So the signal, optical signal propagating from one medium to another, one place to another place by using optical fiber axis. Then it is called a meridional ray. And second one, skew ray. So skew ray, it is a ray that travels inside a fiber in the form of zigzag path, and it will never crosses the axis of an optical fiber. Then this ray is called as skew ray. And the third one, guided ray, or we can say that bounded ray, or we can say that trapped ray. So it is a ray in a multimode optical fiber which is confined by the core. So within the core it is getting confined. For step-index fiber, light entering the fiber will be guided if it makes an angle with the fiber axis that is less than the fiber's acceptance angle. We'll see what is acceptance angle in the forthcoming slides or next video. I will explain in detail about what is acceptance angle. Then fourth method is called leaky ray or tunneling ray. It is a ray in an optical fiber that geometrical predicts would totally reflect at the boundary between core and cladding. So which suffers loss due to the curved core boundary. Then it is called leaky ray. So in ray optics, we have four different ray model or ray method: meridional ray, skew ray, guided or bounded or trapped ray, and fourth one, leaky ray or tunneling. Then look at the diagram. So meridional ray. So meridional ray, as we all know, that the ray that passes through the axis of an optical fiber. There are two different type of meridional ray. One is a bounded ray and another one unbounded ray. So the bounded ray, it is nothing but the ray that propagates through the optical fiber by using the important concept is called TIR, that is called total internal reflection. The next one, unbounded ray. So these are all the rays that are refracted from the core. right? Then cladding imperfection prevent total internal reflection. Then unbounded rays eventually escape from the cable. Then the light entry into the tip of the fiber core. Look at the diagram. The light is entering from the outside world to the fiber core at the axis. That will make an angle theta naught. Then by using total internal reflection, all the signal, all the light entry is getting reflected at the core cladding boundary. So that this will follow the, or we can say that it will obey the Snell's law. So the condition for Snell's law is n1 greater than n2 and theta 1 greater than theta 2, right? So if it is in same plane, then the incident ray and the fiber core should be in a single plane. Okay, then meridional ray, look at the diagram. So this will give you the detailed picture about the meridional ray. So two ray incidents where we have maximum intensity at a meeting point of two ray during propagation. So meridional rays takes a comparatively lesser light ray path because lesser acceptance angle. Because of the lesser acceptance angle, the laser light ray path it is very less. Then these rays are confined to the meridional planes of the fiber, which are the planes that contain the axis of the symmetry of fiber. So this is the representation of the meridional ray. Then next one is skew ray. So as we all know that what is skew ray? So skew ray will never meet the axis of the fiber. So it does not lie in the plane containing axis of the fiber, and it will go in different direction, all the direction. Okay, then the ray will go spiral around the fiber axis. So then we can say that if it is in spiral means what? It will get reflected many places inside the core. So multiple reflection in the interface region. Then light intensity of this ray is very low, so it never meet the axis. Two possible intensity distribution in skew ray is, one is the maximum intensity distribution at the center, that means in the axis of the fiber, and next one it should have minimum intensity at the center. So there are maximum intensity at the center axis of the fiber and minimum intensity distribution at the center where we can have the meeting point of core and cladding. Okay, then the skew ray acceptance angle. So because we all know that the skew ray does not follow the axis of the fiber, so because of that characteristics, we should derive the acceptance angle for skew ray. So this will not satisfy the condition of meridional ray, so that we should derive the equation for the acceptance angle for skew ray. Okay, it depends upon the light collecting ability of the fiber, and it depends upon the what type of source we are using and what type of fiber we are using. So theta naught and theta max is giving the angle. So theta max is equal to maximum acceptance angle, which is equal to sine inverse of n1 square minus n2 square whole power of. So it is called a numerical aperture. It is the main parameter of the optical fiber. Okay, where the numerical aperture should be large as possible. That means you should be large as possible. So if it is in larger mean, then we can collect more number of light from the outside. So here n1 is a fixer, that is refractive index of the core. That is a glass we are using here. Then the corresponding refractive index of the glass, it is 1.5, and in general the n2 value must be greater than or equal to 1. This is a condition we have to satisfy for skew ray. Then, what are all the model analysis in skew ray? So, in the total ray model analysis, the total internal reflection explains that the ray completely reflected at the boundary between core and the cladding. Then, it does not discuss about what happened in the cladding. Why? Because the incident light at the core cladding interface, all the light ray getting reflected back to the core by using total internal reflection, so that we are not at all talking about the signal propagation inside the cladding. Then zero intensity in the cladding. So after crossing the core cladding boundary, we don't want to worry about what is the intensity of the signal at the cladding. So we can say that it is zero intensity, and does not give the correct picture of total internal reflection, because at the interface the electromagnetic field in terms of light will go to zero. Then wave model analysis. So in this Skew Ray, the wave model analysis is at the cladding medium. The light intensity is it's not a zero exactly, but the fields are present in the second medium and it is exponentially decay in the cladding. So at the cladding, we cannot say that the intensity is exactly zero, but it goes on propagating inside the cladding. At some point, it's going to be zero. Then the field in the cladding must be considered, otherwise it will disturb the field inside the core, so that we go for protect the field in the cladding. The proper cladding should be done to diode the field, and that should not go away to the outside of the world. So these three things we have to maintain in the cladding, so that we cannot get any disturbance for the core. Therefore, at the total internal reflection, the standing wave types of fields in the core, and third one, decaying field in the cladding. Then next one, the ray undergo phase changes at the reflecting boundary. So this is a Skew Ray total internal reflection diagram. Now look at that. In this diagram, the signal getting reflected back at the core cladding point, where we can say the point of incidence. Then after crossing the the point in a core cladding interface, getting reflected. So the entire signal or entire light ray getting reflected back to the core, so entire reflected ray. So where the reflected ray and the incident ray making a point where we can have the phase front. So this meeting point is called maxima and minima. In maxima, the intensity is maximum. At the minimum point, the intensity is minimum, so that this will form a standing wave. So the sustained constructive interference by the phase front is achieved by separation between them. Here the separation between these two things by the multiples of 2 pi. Then only the phase front moving in this direction and gets reflected back. Then the continuation for that Skew Ray. So from that we can find out the value of S1 and S2. So S1 equal to D divided by sin theta and S2 equal to AD cos theta. And we can sort out this one, and finally we can reach the equation S2 equal to cos square theta minus sin square theta into D by sin theta. So to get the exact reflection at the core cladding boundary. So these two conditions we have to maintain, then only all the signal getting propagated inside the core in the form of Skew Ray communication. Okay, then for sustained propagation, the incident angle of the ray always must be less than theta max, that is total internal reflection. Then with the above incident ray, that should satisfy the condition of 2 pi n1 d sin theta by lambda plus del equal to pi m. Otherwise, all the signal getting propagated inside the cladding. Okay, here pi and m it is integer value, and the value of 2 pi n1 d sin theta by lambda gives the discrete angle difference, that is the angle should be in discrete form. Then departure from the solid cone of light in continuous theta domain into discrete theta domain. So the signal getting light signal getting propagated inside the core by solid cone angle, where the outside it should be in continuous domain and inside the core it represents discrete domain. So this change will leads to important concept is called modes inside the optical fiber. So discrete value inside the optical fiber, that is called modes. Then Skew Ray acceptance angle. Here the Skew Ray follows a helical path through the fibers. Therefore, the path traced through the fiber gives a change in the direction of 2 gamma into gamma plus gamma. That means each and every reflection we can represent the value, it is the gamma. Many number of reflections going to taking place for Skew Ray. Why? Because this will not follow the axis transmission. So the number of reflection inside the core will give the output distribution, not depends upon the input condition of the fiber. The non-uniform light input, where the uniform light output by multiple reflection. So non-uniform into uniform light conversion. The incident and reflected rays at the point B are in the same plane represented by cos theta. Then thus because of that, many reflection inside the core, where we are going to derive the equation for acceptance angle. So this acceptance angle is derived based on the core and the cladding reflection and the axis between the incident ray and the reflected ray and the distance. So these are all the things we have to maintain, or we have to calculate to find out the acceptance angle. Okay, so the skew ray representation cos gamma into sin theta equal to cos theta by using trigonometric relationship. We know that sin squared pi plus cos squared pi is equal to 1. Then cos pi we are taking. Then we can substitute this value according to total reflection. Pi equal to pi c, that is critical angle. So we can substitute that value. Then we can reach the value of sin theta as. So sin theta as, it is the angle where is equal to n1 square minus n2 square whole power of divided by cos gamma. The main difference between the acceptance angle of the meridional ray and the skew ray, where we have in the denominator cos gamma. The gamma represents the reflection. Okay, then depends upon cos gamma value. The axial angles are larger than meridional rays. So in meridional rays, cos gamma equal to 1 and the acceptance angle is theta a is equal to theta a. So hence, skew ray tends to propagate only in annular region near the outer surface of the core and do not fully utilize the core for transmission. So it will not utilize the core area for transmission. Inside the core, it will get reflected many points, then it form a helical path. Okay, so this is a diagram. You can see the movement of this skew ray inside a core without, not like our meridional ray, it follows the helical path. Then what is the main comparison between meridional ray and the skew ray? Meridional ray enters into the optical fiber through its axis, so axis transmission. But the skew ray enters into the optical fiber not in its axis. Then second important comparison is the ray crosses the fiber axis at each reflection. But here skew ray do not cross the fiber axis and propagate around the optical fiber axis. The meridional ray acceptance angle is minimum, but in skew ray acceptance angle is maximum. Light collecting ability, or we can say light collecting efficiency, is minimum in meridional ray, but here the light collecting efficiency is maximum. Then the path taken by the meridional ray, it is in zigzag manner. Here it is in the helical path. This is the main comparison between meridional ray and the skew ray. Okay, then the fourth one, leaky rays or trapped rays. So the leaky ray, or we can say that leaky modes, or in another way we can say is a tunneling mode. It is a mode having an electric field that decays monotonically for a finite distance in the transverse direction. So transverse direction means what? The perpendicular direction to the axis. So the propagation of light through optical fiber by skew rays suffer only partial reflection, while meridional rays are completely guided within the fiber. These modes are allowing propagation of skew rays are called leaky modes. So the propagation of skew ray above the core, that is inside clad, is called leaky ray or leaky modes, or we can say the tunneling ray. Some optical power is lost into the cladding due to this type of modes, that is called leaky modes or leaky rays. Then we are going for the next topic is called what are all the types of optical fiber. What are all the types of optical fiber? So optical fiber classified into three important characteristics. One is what is the material which you are going to use for manufacturing optical fiber, and what type of refractive index value. Based on the refractive index value, we can have two different types, and how many number of modes the fiber will support. In that way we can classify into two different types. So there are three main classification of optical fiber. One is based on material, where we can have glass fiber and plastic fiber. Based on mode, single mode fiber, multi-mode fiber. Based on refractive index, step index fiber and gradient index fiber. Okay, so step index fiber, it is the one in which the core contain uniform value of refractive index. So there won't be any changes in the refractive index to core. Then it is called a step index fiber. Then it looks like a step, right? Okay, then the refractive index profile for step index fiber, it is n of r. So n of r, it is refractive index profile, which is equal to n1 when r less than a. So that represents core. So in core, the refractive index value is n1. And N2, the R value is greater than or equal to E, that represents cladding. So cladding refractive index is N2. The condition for this one, always N1 is greater than N2. Now look at the diagram, step index fiber. So the inside core, the refractive index will be constant. Outside the core, in cladding, refractive index also, it's a constant N2. Okay. The diameter of the core is about 50 to 200 micrometer in the case of multimode fiber, and 10 micrometer in the case of single mode fiber. and this type of modes contains lower bandwidth and lower attenuation. The light ray propagation is in the form of meridional ray, that is called zigzag path, and it passes through fiber axis. Now look at the diagram. These are all the index of profile, and single mode fiber, or we can say that mono mode step index fiber, and multi mode fiber. That is the mode means what? That path taken by a ray inside a core. So first one, it is single path only, so it is mono mode, and the second one more than one path, then it is called multi mode step index fiber. Then single mode step index fiber. These are all the characteristics of single mode step index fiber. Only one mode it should support, and the diameter it is the order of 2 to 10 micrometer. Then the dispersion, intermodal dispersion is very low compared to other fiber, so that lower tolerance requirement on the fiber connector, bandwidth is maximum, and the main advantage of single mode fiber is larger numerical aperture, larger core diameter, and easily coupling to optical sources. Then multi-mode step index fiber, in the name itself says that multi-mode. So it should contain, or it should support more number of nodes during the propagation, right? So a multi-mode step index fiber has the core radius A and the constant refractive index N1. A cladding of slightly lower refractive index N2 surrounds the core. Okay, so diameter of the core is 50 to 200 micrometer, lower bandwidth, light propagation in zigzag path along the fiber, and it is applicable for only short distance communication. The dispersion is maximum and the performance is minimum, so that only it should applicable only for the shortest distance communication. Then graded index fiber. So graded index means gradually varying. So the refractive index of the core is made up of the very gradual way, that it is a maximum at the center of the core and it is minimum in the cladding. So at the center the refractive index is maximum. When you go away from the center, the refractive index is minimum, that is near core cladding interface. So gradually it is getting decreased. That's why it is called graded index fiber. The diameter of the core is about 50 micrometer in the case of multimode fiber. The path of light is in the form of helical in nature. Then the attenuation is very less. The fiber has higher bandwidth, and the light propagation is in the form of skew ray, and it will not cross the fiber axis. These are all the parameters or characteristics of graded index fiber. Okay, what is the profile? The refractive index profile of the graded index fiber, it is n of r equal to from 0 to a. From 0 to a, the value of n of r is equal to n1 of 1 minus 2 del r by a whole power alpha whole power 1 by 2. When r is greater than or equal to a, n1 1 minus 2 del whole power of, it is approximately equal to n2, where del it is a relative refractive index difference, alpha it is a profile parameter. We can have many value of alpha. If it is alpha equal to 1, that represents a triangular profile. When alpha equal to 2, then we can say that it is a parabolic profile. When alpha is equal to infinity means, then this graded index fiber converted into step index profile. So how we can convert a graded index to step index? By choosing the alpha value infinite. Then this is the structure of graded index fiber. Now look at that. The refractive index is gradually varying. So at the center it is the maximum. When it is to go away from the center, or we can say that core cladding interface is going to reduced. So look at that, the profile diagram. So core inside the core axis, where the signal getting propagated inside the core, and over which we have cladding the value of a n1 n2. So the ray transmission inside the multimode fiber, it follows a helical path. Then the main comparison between step index fiber and step index multimode fiber, a graded index multimode fiber, the bandwidth size of the step index fiber, it is lower, and similarly for the diameter is 50 to 200 micrometer. But when you go for graded index fiber, higher bandwidth, and the diameter of the core is 50 micrometer. Then application scenario, if our step index fiber is applicable only for short distance communication with low speed, but in graded index fiber it is a medium distance, around 10 to 20 kilometer. The data rate and the speed, it is 34 to 140 mbps, that is megabits per second for communication system. Then the data transmission form in step index fiber, this will follow zigzag path, and the graded index fiber, it should form a curved size or sinusoidal form. Then the dispersion. In serpentex fiber, it will affect the transmission capacity of the fiber and limits the relay distance, and here greatly decreased dispersion than the serpentex multimode fiber, making a higher bandwidth. The numerical aperture of serpentex fiber, it is high, and great X fiber, it is low. The reflection losses is there in serpentex fiber, and the reflection loss in gradient X fiber, we cannot say that low. I mean, it should be very low. Then attenuation is maximum in serpentex multimode fiber. Here the attenuation is minimum in the gradient X fiber. So thank you all. Thank you for watching this video. Thank you.